Software Engineering Daily is sponsored by Hired.com. If you're looking for a job, Hired.com is the place to start. I've used it personally, and it is an excellent service. Software engineers and designers can get 5 interviews in a week with top companies. Go to Hired.com/softwareengineeringdaily for a $4,000 bonus upon accepting a job. Thank you, Hired.com. Erlang is a functional concurrent programming language. Joe Armstrong is one of the designers of Erlang. Joe, welcome to Software Engineering Daily.
Thank you.
Erlang was originally designed within Ericsson in the 1980s to support distributed and highly available applications, but more recently it has seen high-profile uses in applications like WhatsApp and Facebook Messenger. So just to set the context for listeners who have never heard of Erlang, it is widely used in modern software. But so let's start out. Why has Erlang persisted as such a popular tool for communication platforms?
It's, I don't know. I mean, it's because it was designed. It was designed to build telecommunications infrastructures with. I mean, it was designed for switching software for telephones. And the nature of that problem is that you have hundreds of thousands of people all talking to each other and all connected to each other. And that's the nature of the problem that you want to solve with massive messaging systems today.
Right. And so we'll get to the present, but first let's go back in time to the 1980s. So Ericsson was surviving by selling the AX telecom switch. It was a really good business.
Yeah.
And Ericsson had its own processor, its own programming language, its own operating system, its own software development environment. Why had Ericsson built all of these things itself rather than using like other software?
But there wasn't any other software when the AXE was invented. I mean, there weren't any alternatives. What were the alternatives? The AXE was the first object, as far as I know, it was the first object-oriented hardware there was in the world. It predated. It comes from a technology from about the AKF about 1974 with the first one, and then Ericsson was making the first. Together with AT&T, the first switching systems in the world. So there was no worldwide net, there was no DNS, there were no worldwide networks. So Ericsson was building these networks and inventing the stuff as we went along.
It's easy for me to take the open source world for granted, I guess.
There was no open source.
So what are the software requirements for a telecom switch?
Highly reliable. I mean, we actually the AXE we had to pay fines if it was down for more than 4 minutes a year. So it was always kind of drummed into you. The whole system hasn't got to crash for more than 4 minutes a year, and you have to roll in the software upgrades without stopping the thing. So it was unacceptable to stop it to change the software, and yeah, those are the main things. Oh, and it's got real-time response, has to respond to things within a couple of milliseconds and so on.
Okay, and so prior to the development of Erlang, Ericsson's programming language was called Plex.
Yes.
What were the problems with Plex?
Oh, Plex was a more or less a sort of real-time basic, if you like. It was more or less, you can think of it as an assembler language. So it had no memory management, and it was very, very difficult to program in. And it was designed at a time when machines had very, very little memory. So Plex programs had to fit into kilobytes of memory and so on. And
how did Plex manage failures?
It didn't do them in software. It did it in hardware. It had 2 processors which were lockstep, and it compared them all the time. And if one processor crashed, it just went over to the second one. So, but if the software was incorrect, that software would crash. But it would only affect one person. It wouldn't affect lots of people, because everybody. It was like a register machine with. Each user had their own set of registers. These were hardware registers. So a Plex exchange could have 100,000 users, or and each user would have their own set of registers. So their software would crash. And hopefully it wouldn't crash anybody else's software.
Okay, so in the 1980s, while searching for a replacement to Plex, there were lots of experiments within telecom with different languages. There was Lisp and Prolog and Parlog and some others. And in the domain of telecom, what were the valuable features of these different languages like Lisp and Prolog?
I think the automatic memory management, that they were garbage collected languages and that they were symbolic languages. So you never lost control. And you didn't have absolute pointers and things like that, which makes changing the code rather easy. If you have language with statically allocated memory and in particular pointers, it's very difficult to move the code and to manage applications. Basically, you want kind of pointer-free languages so that you can move things. If you've got pointers, you have to move all the pointers, and you absolutely don't want the pointers pointing off the machine because what they point into might crash or might not be available. So you have to.
What kind of concurrency support did these languages have?
None at all. I mean, Prolog and Lisp and so on aren't concurrent languages; they're sequential languages.
Okay. Well, and so I guess that raises a problem because one requirement for good telephony is that you have this granularity of concurrency.
Yeah.
Like I think I read, you wanted one asynchronous telephony process that could be represented by one process in the language.
Yes. Yeah. I mean, for each asynchronous activity that you observe in the real world, you want to map that onto one process. So if your problem requires you to have 1 million processes, then you should have 1 million processes. It shouldn't be a kind of software penalty that says you're not allowed to have a large number of processes. Most programming languages don't have concurrency. They don't have any notion of processes or anything like that. And so they use the concurrency mechanisms that are available in the operating system. And they're very coarse grain and they're very, very expensive. So you get a bit of a mismatch between what you'd like to do and what you can do. So basically, virtually all programming languages are sequential, and that they force you to think about the world in a sequential way. That's why they're not appropriate for programming problems where there's a lot of natural concurrency.
So was Erlang shaped by these two? Like on the one side, you had these experiments with Lisp and Prolog, where you see, there's automatic memory management and symbolic logic. But on the other hand, we have this requirement for this one-to-one mapping of telephony processes to language processes. Was it the merger of those two ideas that shaped Erlang?
Yeah. And then I mean, I was when I joined Ericsson, I didn't have any experience with that kind of thing. So there were older engineers. There was a guy, Sever Torstendal, who'd designed a Eri Pascal, which was the version of Pascal with parallel processes. And he kept wandering into the lab and so, no, it's got to do it this way. And we tried that, didn't work. Do it this way. I mean, all kinds of things like whether message passing is synchronous or asynchronous, or all the kind of semantics of what happens if you send a message to something and, it existed when you sent it, but it died before the message got there. What should you actually do? And the kind of semantics of those things were, people had thought about that for a lot longer than I'd thought about them. And there was a kind of tradition of we'll do it this way and it should work. Try it this way. And we tried that and it didn't work.
So did your naivete help with your development of Erlang?
Probably. I should think so, yeah.
Interesting. Can you talk more about the...
Because, of course, I mean, you say when you developed Erlang, because that's a kind of after the event reconstruction, because at the time I didn't know I was doing something that would blossom in the way it did blossom. I mean, you don't think you're just doing experiments with a different way of programming, and you don't really imagine that there wasn't even a language to start with. So it became a language.
Yeah, I mean, that sounds really interesting. Let's talk more about the creative process. I mean, how did Erlang germinate?
Well, actually, we had a MD 110, which was a PABX, private automatic branch exchange, a small telephone exchange. It which a guy called Per Hedeland had modified some hardware so we could control it with a VAX 11750. And we put Berkeley BSD on the VAX. And then basically we said, okay, so let's just get every programming language we can find that will run on a VAX or on a Sun workstation, because we also had some Sun workstations, and just try and program telephony and just see what the programs look like. So we did that, and that was a lab experiment. There were 4 or 5 of us involved, and we each chose 2 or 3 different programming languages, and we programmed the same problem, and then certain patterns kind of emerged, and I got thinking. I was actually, well, it was a bit of an accident, really. I made a model of telephony in Smalltalk because I liked this notion of Smalltalk. Smalltalk's got objects and you send messages to things. At least that's the abstract model. You don't really do that. You make method calls. And I ordered. I was running this on a Sun workstation, and it was so slow that when it garbage collected, I literally went and took a coffee break because it took about 20 minutes to garbage collect. So you'd run this program and it would garbage collect. So, I'm going to have a cup of coffee. And I got fed up with this. So we ordered a Tektronix Smalltalk machine. It's one of the first hardware Smalltalk machines. And it had a long delivery time, about 3 months or something like that. And during the time, while I was waiting for it, I didn't do any more Smalltalk. And I was just using the Smalltalk notation on the blackboard to describe how this worked. And then another guy said, well, that's almost Prolog. Because it was a sort of algebra I'd made. And he introduced me to Prolog. And I didn't know Prolog. So I rewrote it all in Prolog. And then I thought, well, that's very nice. But the trouble with Prolog was I could only describe one call, and we got dozens of calls going on in parallel. So I thought, I'll modify Prolog so that it's got some concurrency. So I just made a meta interpreter in Prolog and made it a sort of parallel Prolog, and that was the start of everything. I was also thinking about errors a lot, because I thought errors. I've never thought you can get all the errors out of a system. When you build it and test it, it's going to crash at runtime. And so I was thinking you need pretty sophisticated ways of covering after you've observed an error. I mean, I've just given up the idea of getting rid of the errors while testing, or for any formal methods. They're just not up to it. So I thought we need all sorts of hooks to sort of be able to introspect errors after they've occurred and put the system into a safe state. So it's a kind of combination of that became Erlang.
And was there a certain point where these, like this loose collection of ideas, cohered into like a clear spec for a language?
No, not really. It sort of, it kind of converged. There's never really, this might sound strange, but there's never really been a clear spec of the language. There's always been a sort of understanding of what it did, and then we had some formal methods people trying to write a really formal spec of it, and they gave up. It's too difficult. There are some really deep problems.
What are the deep problems? Why can't you formalize the spec?
Well, you can. Well, you can approximate. You can approximate it, right? But you probably couldn't write a fully because you run into impossibility pretty soon. There's I must put this into some of my lectures. There's a nice motto. You might have heard it. Let me think. It goes like, you say, exactly once is impossible. Have you heard that? Exactly once is impossible.
I think I've heard that.
Do you know what that means?
Exactly once processing
it's
possible?
If you send a message between two processes, to guarantee that it is sent exactly once is impossible. So it's quite easy to see. There are two things that are possible. At least once is possible, or at most once is possible, right?
Is this like the Byzantine generals?
Well, it's like if you imagine a message going between two systems, in order to make it fault tolerant, you would have to have a log, right? So you can log after the message has been written, and then you write to the log, and then afterwards, and you write to the log before you write it, and you write it, and then you look in the log, and if it crashes, you go back and you look in the log. And if you examine all the scenarios where it can crash, you find, wait a moment, this if it crashes before we've written to the log, or if it crashes afterwards, you just can't do it. So, I mean, to get at least once is easy. I mean, if you send one message, right, it'll either get there or it won't. So that's, sorry, at most once. So it's either 0 or 1 times. Yeah, that's quite easy.
Right.
And, sorry, that's at most once. At least once is also quite easy. You just send loads and loads and loads and flood it with messages until you get some response. And then you know that it was at least once. I mean, it might have been a dozen, but you have this continue. But exactly once is impossible. So when you go from sequential programming, where exactly once is everywhere, right? When you call a function, you have no trouble proving that the function got called once. But when you replace that by a remote procedure call, the semantics of it change radically and turn into something that's impossible.
Okay, I see.
So suddenly you have, if you're trying to write down the semantics of message passing and things like that, you run into all sorts of problems. So for example, people ask questions like, there was a very nice question on the mailing list that said, is message passing between Erlang processes reliable? And Per Hedeland, he was the guy who he said, he wrote back and he said, yes, if you believe that TCP is reliable. so you always kind of got this like, well, is message passing reliable? Well, yeah, if you actually, does anybody believe that TCP is reliable? Or does that, well, do you believe that two-phase commit or three-phase commit or 10-phase commit is proof that something's happened? No, because mathematically infinite phase commit doesn't work. So you run into these kind of black holes of complexity, which you don't see you see a completely different set of problems when you're building distributed systems.
Yeah, you certainly do.
And if you want to kind of write those down in a formal way, things like leadership election are suddenly, the Paxos algorithm and things like that, are suddenly very, very difficult.
Yeah, did you anticipate distributed computing was going to become so important and so difficult when you were writing Erlang?
No. I mean, there were lots of sort of nice surprises that came later. Oh, look, we can program multi-cores. They just sort of work. They just kind of work. And I think what I didn't realize was which only came later, was the realization that architectures that allow things to be fault tolerant are exactly the same as architectures which make things scalable. Because, if you want to make things fault tolerant, you make lots of small isolated things which are completely independent. And if you want to make things scalable, you make lots of isolated things that are completely independent. So architecturally, they're very, very similar. In fact, I now view them as exactly the same. And that was, then I learned later that the tandem computer was built for fault tolerance. This was in the mid-'80s. And it actually found its biggest markets in building scalable systems, not fault-tolerant systems. It was designed for fault tolerance. It was used for scalability. And that's exactly what's happened with Erlang, the kind of WhatsApp and things. They're not using it for the fault tolerance. They're using it for the scalability. And it's because the design method forces you to, it's really rather simple. When you design something, you just break it down into processes based on the natural concurrency. So you might start off with one process per user. It'll usually be more, say, when we're doing telephony, it was 6 processes per user. So, and then you say, okay, so 6 processes per user, they're pretty well localized. And then you say, well, how many processes can I run per processor? I don't know, maybe 1 million, 2 million, 3 million processes per machine, per physical machine. And then you put that on one machine, it's maybe a 4-core, 8-core machine, and the Erlang runtime will just sort of move these processes around onto the cores. And you don't need to worry about that kind of thing. And then you just partition it and put these, say put, what's that? You've got 1 million processes and 6 processes per user. You say 160,000 users per machine or something, and then we need to dimension it for 1 million people, so buy 6 machines. There's a bit of plumbing to wire it all up, and there you go, it's working. Want 10 million? Just it scales horizontally. Then once you've got that architecture, but you need that architecture. If you didn't have that architecture, you'd be. It's like Node.js or something like that, which doesn't have that ability. You see, you're putting everything into one process. So when your machine isn't powerful enough, you've got to partition the problem, and you go, oh dear, how do you do that? So it's that partitioning is done early in the Erlang design process.
Yeah. So let's talk more about the language level concurrency within Erlang, like how the programmer implements concurrency.
Yeah.
Can you give a high level description for how the programmer should be thinking about concurrency and how the programmer models things?
Well, there are. Yeah, I mean, it's ridiculously easy. I mean, you've got 3 primitives. You've got spawn, creates a parallel process, and it returns a process ID. And then you've got send, 2 arguments. The name of the process and the message you want to send to it, and you got receive. Receive is just a set of patterns which pattern match over the thing you send. So that's it. There's no locks, there's no mutexes, there's no threads, there's nothing, and all the processes have their own private memory. They can't access each other. No dangling pointers, and no guarantee of message delivery. So I mean that's pretty much how the world is. So if you can. That is actually true object-oriented programming. If you think about it, I mean, I would claim that Erlang is the only object-oriented language there is.
Really?
Yeah, because all Java and C++, they're not object-oriented.
Why not?
They violate isolation. Objects are supposed to be isolated. They're not. Erlang processes are isolated. Well, you can't. It doesn't matter if you can put 2 applications in the same workspace and one destroys the other in some sense. They're not isolated.
Okay, I'm still not clear what you mean. What makes Java and C++ not object oriented?
But because they don't have. See, because they don't have processes to start with. They're objects. Their objects aren't true concurrent objects. It's okay, provided you don't. If you want to model something like time or a clock, something goes wrong inside them. Think about concurrent programming in Java. It's horrendously difficult.
Yes.
Concurrency, shared memory, all these things don't go together. If you want concurrency, you might as well throw shared memory out of the window, because you can do it, but it's just so extraordinarily difficult that virtually nobody can get it right. I mean,
okay.
We're quite happily using a message passing paradigm, aren't we? Here you are, you're in America somewhere, and I'm in Sweden, and we're talking. So we can model the talking as messages, yeah. And I don't know what's in your brain, and you don't know what's in my brain. Just imagine the complexity if we had to, we were sort of forced to have our brains somehow kind of surgically conjoined so that we could see each other's thoughts. I mean, it would be terrible.
It's true. Okay. So, but also in terms of Erlang, so every process has a mailbox, and the mailbox is like a queue of messages that have been sent from other processes.
That's right. Yes.
What's the interaction between a process and its mailbox?
Well, it's that receive primitive. Send sends a message that gets put in the mailbox of the process you sent the message to, and receive is just an operator that goes and looks in the mailbox. And so if I say receive a symbol ABC or something, it's just like the guy walking out to the post and looking in his mailbox. And is there an ABC in it? Yeah, there is. So it lifts it out of the mailbox. Got
it. So could you give maybe an example for what types of messages? I know this is a naive question, but what types of messages you would want to send between different Erlang processes?
Anything. I mean, it's higher order. You can send functions. You can send data. You can send an entire database in a single message, or anything you feel like. There's no marshalling or unmarshalling, or no. It just works. It's really simple. send anything you feel like. The entire operating system, or messages can be anything from, you could say, tell me the time of day, or what time is it? And it says it's 2 o'clock in the afternoon, or send me an entire operating system, or it's a gigabyte or whatever. It doesn't matter. Just all works.
Yeah. So Erlang also offers dynamic code upgrading, which means that you can change the system code itself without stopping the system.
Yeah.
How is this implemented?
This is one of these kind of bugs, I think. Every module has, if you're familiar with a language with objects or modules or anything like that, in Erlang, you can have 2 versions of the module, right? And depending on the syntax of how you call a module, you can get the version of the module that you used when the first time you called that module, or you can get the latest version. But there's only those 2 options. So if you start off with let's call a module X, and have one process and it's calling this module X, it will use the module X, and then I start a second process and I change X. I put a new version of X in. I can still call it X in the code. The first version will be using this old version of X, the original version, and the new process will be using the new version of X. And the 2 will never get confused. Okay, so that allows us to inject new code into the system without changing the names of the modules. And they can behave differently. Because we didn't want to the reason for that, we didn't want to change all the system software when you're making an upgrade. You've got a module called foo or something, and it's got 500 routines in, and you decide it's wrong, and somebody's running this stuff that calls foo, and then you want to start a new bit of software that's also going to call foo, but foo was slightly wrong. We don't want to you could change it to foo1, but that would be an awful mess. They'd have to change all their software. So we just call it foo, and then there's some namespace things. Now, what's wrong with that? I mean, it works fine. It was that the restriction of having 2 versions was due to the fact we implemented this in 1986. If I had to do it again today, I would have an indefinite number of versions and just garbage collect away the ones that you can't reach anymore. So basically, when you start a process and you go get your code, you sort of freeze that code in, and you'll run with that until you die. And then a new guy coming along and he starts a process, he'll get his new version of the code. They might all have the same names as the other version, but they could be different. And that's just to make life easy. Well, it works very well, actually.
Yeah, definitely. I mean, so getting back to the kind of historical story, once Erlang was developed, what was the process to replace Ericsson's systems, or at least the Plex systems, with Erlang?
There wasn't a process. It all happened by accident. There was a very large project called AXEN to do exactly what you say. There wasn't a project to replace the programming language. That would imply that you were going to keep the hardware the same and change the programming language. There were never projects like that. What there were large projects that were basically going to change everything. They were going to change the hardware. They were going to change the software, the whole infrastructure, because the technology was kind of moving forward. So there was a massive project called AXEN. The N stood for new, the new AXE, where they were going to build new hardware and new software, and they were making their own. They were going to use C++, and because C++ has some problems with changing code dynamically, they'd made their own thing called Delos and a few other things, and that project was running in the same building as we were doing our work. The computer science lab and this project were in the same building. After 6 years, that project collapsed and just didn't work. The software didn't work. So they restarted the project. And the hardware they'd built was okay. And we'd borrowed some of the hardware and had built prototypes in Erlang at the same time. And so at that stage, they said, well, we'll keep the hardware and we'll do it in Erlang. And they did. That became the AXD 301. And that was really the kind of breakthrough for Erlang inside Ericsson. But as I said, that relied upon two accidents. One was the collapse of this big project. And the other was that we knew about the collapse. The only reason we knew about it was we were in the same building. Okay, and we knew people. If Ericsson's got big places all over Stockholm, and these were both south of Stockholm, if we'd been north of Stockholm and the collapsing project would have been south of Stockholm, we wouldn't have even known about it. I mean, there are kind of barriers between divisions, so you don't really know what's going on. But we did know about it, and that happened. So that was the point at which it got adopted, and it wasn't because there was some plan to phase things out and phase new things in. It was a sort of, we've got a catastrophe. Help! What the hell do we do? We can, it's a drowning men clutch at straws phenomena.
Necessity is the mother of invention kind of thing. Well,
actually, I should point out that I didn't form the lab. Mike Williams, one of my collaborators, was one of the original formers of the Computer Science Lab, and I joined it when it was 2 years old. And Bjarne Dekker, he was the head of the lab, and we were very naive because we thought that we thought the sort of job of technology transfer was okay. So we do some research into Ericsson's problems. We hopefully invent some stuff that would make better solutions. Engineers sit round a table and we all argue with each other. And if our solution is best, they'll use it. That's what we thought would happen. Doesn't work like that at all. There's company politics and all sorts of things involved.
Yeah. We'd like to take a moment to thank our sponsor. DigitalOcean offers simple cloud infrastructure for developers. In one click, you can have a mean stack, a Rails application, an Ubuntu box, or another custom environment. Software Engineering Daily is proud to have DigitalOcean as a sponsor because DigitalOcean is the simplest cloud service provider. I've interviewed Moise Uretsky, who is a founder of DigitalOcean, and he told me that DigitalOcean was based on this realization that other cloud service providers are so complicated. If you want things to be simple when you deploy your application, use DigitalOcean. To try DigitalOcean, go to digitalocean.com and enter promo code SEDaily. That promo code is one word, SEDaily. Now let's get back to our show. Let's zoom out of history a bit and talk more about the language itself. So Erlang is a functional language, and speaking broadly, what are the advantages of a functional programming language?
That you don't have mutable state. I mean, mutable state's the root of all evil. It's terribly difficult to reason about programs with state. State's horrible. So.
But state is a must-have in certain situations. So where is it about isolating the state in the database, or what exactly?
If you're forced to design in such a way that you have little mutable, destructive state. I mean, it's mutable state where it's okay to change state and then you only use the latest value. Single assignment, that's like LOVM uses single assignment. What's bad is using the old state, right? Because you don't know how long it persists and you have trouble getting rid of it and so on. So your job really is to design it so that this destructive state operations are used minimally. And you want to kind of design methodology that does that. And when you do mutate state, you want to do it in a very controlled fashion so that you see exactly what's going on. So yes, large functional programming will have little kind of dirty areas where things are not very nice, and I really want to keep that to a minimum.
So is this why managing concurrency is easier within a functional language?
It's one of the. It's not the only reason. It's one of the reasons. Yeah, I mean,
what are the other?
Well, if you don't have mutable state, you don't. I mean, a lot of concurrency have problems with locks and things. You have to lock your data so that two people can't mutate it at the same time. But if you can't mutate data, you don't need any locks. You see, so a whole lot of problems just vanish. It's not like it's not like you solve them in a different way. You don't need to solve them at all because they don't exist. It's a different way of thinking.
So you mentioned this a bit earlier, but what are some of the problems with object-oriented programming, and how do those get fixed in moving to functional languages?
It's all this state in objects, and also concurrency, because you see, you like to the object, the way you teach object, or the kind of conceptual model is you send messages to objects, right, and they have private state, and their state changes, but they do this synchronously. They don't do it asynchronously. If you send them, and then they're actually not messages; they're disguised method calls, they're subroutine calls, right? So if you send a message to an object, i.e., evoke a method that takes a very, very long time, right? You have to wait until that terminates before you go and do something else. So you don't have any natural concurrency there. So really, if you had a million core computer, which a colleague of mine said we'll have in 2019, and you have a million processors, a million objects, you would put one object on each core. They'd be nicely isolated. They'd all run in parallel. But you don't have languages that, well, you do that in Erlang, but you couldn't do that in Java. You couldn't take each instance of an object and stick it on a completely separate processor. Just wouldn't work.
Why did object-oriented programming become so prevalent and so widely used?
Probably because it's flawed. You see, if I remember the it's very difficult.
Do you think it has to do with business requirements? Like, object-oriented programming is easy to communicate business requirements with.
No.
You don't think so?
No. I think Gosling said something which was very good. He said at some stage, he said, Java isn't a programming language, it's an industry. And I think he's exactly right. That he put his finger on it totally. Java is an industry. Erlang is a programming language. There's a difference. Because, viewed as an industry, Java has everything, right? You can buy embedded processors that can be fit on a wafer or something like that. You can put them, you can etch them onto paper you can make bus tickets out of them and boot them in a few seconds, or you can build a server farm with them. You can hire consultants, you can embed them, you can do everything. You can hire consultants, a lot. Erlang's just a programming language, I'm afraid. It doesn't have all these other things.
So, I often see Erlang used as a message passing layer between other languages like Java. How is that language interoperability typically implemented, and what's the motivation for it?
Through a serial. I mean, basically, Erlang refused. You're not allowed to link. One of the things we're kind of religious about is Erlang when you interface it with something, you shouldn't link foreign code into it, right, into its kernel. Because if there were mistakes there, you can crash the Erlang system. So Erlang will only communicate through ports, which are just serial communication channels. So you have to serialize your data and parse it and unparse it and agree on some framing and some protocol. You might send JSON, or you might agree, okay, so we'll use TCP and we'll send JSON messages or something like that. And then both sides have to implement that.
Right, got it. So functional programming seems to be exploring something of a renaissance these days. Why do you think that is, or do you see it that way?
Oh, yeah, I agree. I think the fundamental problem we have with software is complexity. The control of complexity has always been the key problem that software engineers look at, and the systems we are building are just more complex. So we need more powerful tools to understand them and build them.
Yeah. You think
also, I think the availability. I mean, if you go back to I think it's about the mid 80s or 90s that I remember language with garbage collection like Java. When Java first came, the notion of using a garbage collected language for anything was very suspect. People, we can't use garbage collection; it won't be fast enough. Well, nobody says that today. You see, so you have to remember, machines are they. I mean, I don't know what the clock rate on this machine is I have in front of me. It's probably sort of 2.5 gigahertz or something like that, or no, maybe slower, 1.8 gigahertz. But I mean, it would have been 4.6 megahertz in 1985. So that when the clock rate goes up by a factor of 1,000, and the memory goes from, the machine we developed Erlang on had a clock rate of about 4 megahertz and about 4 megabytes of memory. Right. So you throw that on a machine with a 4 cores, 2 gigahertz clock, 16 gigabytes of memory. It is literally millions and millions of times faster. Okay. So things that were slow can now be done very quickly. Now, functional languages were slow. The implementations are slow. You're doing a lot more work in the background to protect the user. You're running garbage collectors. You're doing all sorts of things. So these assembler languages like C and so on, they are, of course, a lot faster, but we don't need the speed. There's very few applications that need speed. And then I see C as being in a nowhere land now, in C++, because from what we know today is if you want to go fast, you should go down into hardware. Use FPGAs or Verilog or something like that and build a custom chip. And if you want to build an application, you can use some, use Python or Ruby or Perl or goodness knows what. I mean, they're fast enough. So where's C? Because if you want to go really fast, you're going to go to hardware. Point. And if you want to go, if you're building regular applications, just use a scripting language. And then I see we've sort of sorted out what we need. There was this period of confusion, I think, in the 90s or something like that. We didn't know which video standards and which video chips and which wireless chips to put in. And then the things come along and you see a technique shift. So for example, Ericsson invented Bluetooth and now you see Bluetooth. It took quite a long time to adopt. But now you see Bluetooth sort of popping up all over the place. And I don't think there's going to be another technical shift because I don't know which problem it would solve. Bluetooth's good enough for audio and video and communication within about 5 to 10 meters. It's fine. And I remember the Bluetooth people saying, well, Bluetooth will dominate. And they said, why? And they said, well, because a Bluetooth connector is cheaper than a physical connector in terms of raw materials. I mean, a physical connector is made out of copper and whatever, and a contact. That costs money. The chip is cheaper. It uses less raw materials. So ultimately, it's going to win through, and it's better than a physical connector.
How has the Erlang community changed over time?
Pretty radically. I mean, it was up to Erlang being open source. It was just entirely inside Ericsson, and with maybe 100 universities or so we had got used to send it out subject to a non-disclosure agreement, and then it became open source, and then it became a community and so on. And then, so I mean, now there's many times more users outside Ericsson than inside Ericsson.
Yeah.
So that changed with open source.
So speaking of Ericsson, one of your colleagues from Ericsson, Michael Williams, wrote that software development is an art, not a science.
Yes.
And if you are going to produce art, you need the best tools. Erlang. Are there any aspects of this quote that you disagree with?
No, absolutely. I mean, I view programming as a craft. I mean, it has all the aspects of a craft. You have to learn it from experts at it, the masters. You study at their feet, and it takes a long time to do it. I mean, it's not the, and I think the difficulty is not in learning a programming language or anything like that. I mean, you have first of all, you've got programming languages. Once you've learned a few of them, you pick them up pretty quickly. But you don't know the libraries, and you don't know how to go about building something. And that takes a long time to learn. And then once you've learnt that, there are different ways of thinking about systems. I was quite funny. I was talking to a colleague of mine, Christian Schulte, who's made GE code, and he's possibly the world's best constraint logic programmer. And we're talking about how you think about problems. And I was saying that, well, if you were an object, I also talked to Simon Thompson, he's a functional programmer. So how do you break down problems if you're a functional programmer? He said, well, functional programmer said, you think about the types first. You think about the types. What types am I manipulating? And then you think about the functions that manipulate instances of these types. That's what a functional program does. And if you're object-oriented programming, you say, what do you think about? We think about objects. Which objects do I have in my system? What method should they have? And so on. And then I thought, well, what do I think about first? I think about the concurrency first. I think which concurrency, what is the concurrency of my problem? That's the first thing I think about. Which thing do I represent as a process? And then I think if you were a Prolog programmer, you say, what do you think about first? You say the relationships. That's the first thing you think about. And I thought, and if you're an imperative programmer, what do you think about state? And then I asked Christian, and said, I thought I'd covered them all. I said, what do you think about first? He said, the constraints. That's the first thing I think about. What are the constraints in the problem? So I think these ways of thinking are difficult. So if I've been programming, for 40 years, so once you've been programming that long, it's all very well to say to a newcomer, well, for every problem there's a best language to use, which I kind of believe, and you should choose the best language that's appropriate to your problem. But if they only know Java, how can they do that?
I guess that's
you look at me and sort of, if I know 15 programming languages, so I've got to solve that. I'll do it in Prolog, do that in Lisp, do that in whatever, So what do you say if you only know one language? Use a Java, use a mini CanRem or something like that, or use a sort of library that simulates logic programming inside your Java.
So you're clearly kind of bearish on Java. Are you also bearish on the JVM languages like Scala?
I'm horrified by. I go to big conferences. I'm fortunate enough to be invited to these conferences, and the big commercial conferences. I see two enormous waves of people wandering around, and they're going JVM, 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 and they go to all the JVMs. So they're interested in languages that run on the JVM. And there's another lot going around .NET, and they go there. And then there's a small number of people who can build, they can build their application on anything they feel like. And I meet so many people who say, "Oh, I'd love to program in Erlang, but I can't." Why? Well, because our company, the language you have to use has to be a JVM language because they deploy everything on the JVM. And I say, "Why is that?" Well, our sysops don't know how to install anything else. It's tragic. So everything gets implemented, at least twice, for JVM and for .NET, and it's exactly the same stuff.
So maybe this is
it's Microsoft. It's Microsoft and Sun Microsystems trying to lock you into their pathetically bad infrastructures.
Yeah. Is this related to you gave this presentation called The Mess We're In, and you argued that software is getting worse over time. Is this one of the reasons why you think software is getting worse?
Yeah. Well, it's a very big reason. I mean, the manufacturers lock in, and their refusal to sort of collaborate with each other is terrible. And also, I mean, a book I read a review of called "The Tyranny of Choice." I mean, it's absolutely dreadful today. If you look at, I was just trying to work out the combinatorics. If you wanted to build a web application, you say, well, I need a CSS framework. Okay, so you thought, oh goodness, how many of them are there? 100? You go and Google CSS frameworks. You'll find web pages saying the best 100 CSS frameworks. Goodness, or the best 10 or 15, and then you want What else would you want? Oh, you might want some sort of graphics stuff or some reactive framework. There's 15 of them, and you might want a programming language. Well, how many programming languages have we got? 2,500? Start multiplying all these together. The number of CSS frameworks times the number of reactive frameworks times the number of programming languages times that's your decision space. It's vast. And so, of course, people then have this anxiety about, well, have I chosen the right framework? Oh, goodness. So I've given up all. I mean, I always get criticised by my I was going to do some graphics in the browser, and I thought, there's only one thing I like, actually, scalable vector graphics. And I thought, I always go into this kind of mental loop and it starts like this. I think, yes, I want to do some graphics in the browser. I don't know much about that. Wait a moment. Somebody must have, I'll search for SVG frameworks. So I search for them on the net, and I find there's 15 of them. Oh, goodness. So I start looking at them. And every single one has got its little church of people who say, oh, this is really great. This is fantastic. You should learn this. And you choose one of them, and you start learning it. And then you find there's something you can't do. Oh, shit. And then oh dear, I chose the wrong framework. And of course, you feel guilty about it because there's so much choice. So if you made a wrong choice, it's your fault. It's not their fault. They've been ever so helpful in making all this stuff available. So it must be your fault if you can't.
Okay, but I'm not clear, because are you more concerned about the paralysis of wide choice, or are you more worried about the constraints of lock-in?
I think both, because then you get to a mental mindset. There are certain, if you like, what appear to be received truths in management and in programming that I just think are totally absurd. One view is that writing something from scratch yourself is going to take a lot longer than using a framework that somebody else has made. And I always think it's fine if frameworks and libraries, they represent abstractions. If you understand exactly what those abstractions are, and they can save you a lot of time. But if you don't really understand what they are, I mean, programming by Googling is not a very good way of solving problems. I mean, it is absolutely dreadful way of solving problems. So I think I was trying to learn Swift. Do you know Swift? Have you tried the latest version of Swift?
I haven't tried it. I know what it is.
Yeah, don't. I mean, goodness gracious me. How can Apple release examples that don't even compile? You get the consistent set of things and you click on them and they don't even work. I mean, and how can you make radical changes between two versions of the language without telling anybody? It's dreadful. Basically, you have one school of programming which is not based around the idea of a small number of primitives which you combine. You have large libraries which export thousands of primitives, and you kind of Google looking for the solution to your problem. And that's a way of locking people into these products, which is very bad. So as I said now, it's got 3 primitives for concurrency. It's got send, receive, and spawn. Okay, there aren't 1,000 primitives, and they're very easy to learn. So back to my JavaScript example. You see, I quite like writing JavaScript, but my interaction with the DOM, I use 2 things. Document.getElement by ID, and returns an ID, and then you can do x.innerHTML equals something. That's easy. I know HTML. I know. I only need to. That's the interface between JavaScript and the DOM that I need. I can hit everything with that. And then I just write my own libraries. And people look at me very strangely and say, you write your own frameworks? Yeah, I'm a full stack developer. I make the bloody programming language of the libraries, the frameworks and everything. And they say, oh, you're going to take you a lot of time. No, it's quicker, I think. That's why it's a craft. I'm one of my hobbies, I'm learning leatherwork. And it's really nice because the tools I use are, one of them's, I talked to the guy, the actual tools I'm using are hundreds of years old. They haven't changed for hundreds of years. It's quite nice to use things which are hundreds of years old. We're not using tools that are hundreds of years old. We're using tools that were made last week. They don't work.
It's true. Yeah.
So somewhere we've got to change. when I started programming, I could choose. Well, I couldn't choose at all. It was Fortran or nothing. That was the only language you could use. So there's no kind of decision problem there. Just imagine how nice that would be. Can you imagine?
Yeah, well, I mean, it's interesting because Erlang has become the time-tested thing that people choose for a certain a certain well-defined vertical, and it's the thing you use. So that's certainly a good sign, at least. So okay, I guess to close off, I mean, what drives what you're working on these days, and what are you focused on?
The stuff that. Well, I wrote a PhD thesis, and that was entitled "Making Reliable." I can't remember the exact title. Making reliable software from something components that can fail or something like that. I go back to what von Neumann and Turing said about von Neumann was thinking about software elements or computers as biological things that would fail and would evolve and grow. And my particular, what I specialized in was in fault-tolerant software. So Erlang is, if you like, the answer to a question, but you don't ask me what the question was. So what was the question? The question was, how do you build software that is fault-tolerant in the presence of software errors? That we know we're going to write buggy software, but despite that fact, how can we kind of get around that? And so my interest has been on building systems that work, basically, that work all the time, forever. And my notion would be that you turn it on and there's no off button because you'll never turn it off and it'll run forever. And you won't stop it and change it; it will evolve with time. And so I'm totally horrified by all this software that just doesn't work. It doesn't work, and the number of devices which it's rather strange because among my non-computer friends, they because I'm a professor of computer science, they ask me questions which they think they're kind of, well, I don't know how this stuff works, but somebody knows how it works. So Joe knows how it works because he's a professor, right? And so, I feel terribly frustrated in having to say, well, have you tried rebooting it? That is not, the highest pinnacle of functional programming is, well, if it doesn't work, just pull the power cable out, power cycle it. Because that's what computing has been reduced to. That we have so many devices and you phone up support and they say, have you rebooted it? We had fibre installed in our apartments about 2 weeks ago, and the guy who they spliced on the modems, and mine was one of the ones that didn't work, and there's some lights on the panel, and the engineer bloke, the guy who was installing it, came in and he cast an eye over all the lights, and all the lights were green. One of them was blue, and the others were green and something. And he said, "Oh, it's all working." And I said, "No, it's not." And he said, yes, it is. Look, the internet lights up. I said, the light might well be shining, but it doesn't bloody well work, I said. and he said, yes, it does. He thinks I'm an old fool. He said, well, you connect your computer into it and show me what I'm doing wrong then. And he connected his computer. He said, that's funny. It doesn't work. So that's what I told you. So we have a reliance on now, it didn't really matter when you only had one thing that didn't work, but now we daisy chain them all together. So, now we have long sequences of things that rely upon the next thing that it functions correctly. And I'm collecting sort of horror stories from some of my next lectures or books. I don't know if you've seen the ones about, the smart light bulbs that got hacked and the smart.
No, I haven't heard about those.
Oh no, there's some company making smart light bulbs, and they were using AES 128 encryption. So some hackers managed to hack the firmware in the light bulbs, and by that listen to the Wi-Fi net, and thereby get access to the entire Wi-Fi net and steal all the passwords and things on the Wi-Fi nets.
Great.
Well, it's lovely, isn't it? I mean, we're moving there to this Internet of Things where virtually the other one was the smart kettles that got hacked.
Yeah, I had an interview with Vince Cerf, and he was talking about how one of his biggest concerns is like refrigerators DDoSing a bank. Like, you don't want that to happen, but that's a potentiation in our future.
Well, one of the things that I saw Vince was worried about was I was saying to my wife, I was saying, golly, because we got this new computer. Do you know where I've got all my, the family? I'm the responsible for the computers in our household. Guess why? So I set them all up, and my wife uses them, and she, oh, that's great. It all works. And so she happily looks at family photos and things. And so, well, here, if I were to drop dead, would you know where all those photos are? How you access them? The passwords you need to get into Dropbox. And, oh no. Oh dear, I better write all these down. And then I said, well, hang on. When we're both dead, will our ancestors be able to find these photos? Because she's interested in genealogy, and we have all these old photos of people from, from when the first photos were taken, old withered photos, and on the back it's written who they are and things. In 2 generations' time, are people going to find these digital photos? I don't think so, because we're paranoid over security now because of the Snowden revelations and everything. So not only will our cloud providers provide us with storage, they'll also encrypt everything like hell. So how are we going to get these crypto keys to our great-great-grandchildren? Anyway, they haven't been paying. Oops, no. Sorry, your account has expired because your great-great-grandchild didn't pay for it. So we're going to lose history. Vince Cerf was concerned about that as well.
Yeah, this is the internet dark age, I think.
Yeah, I mean, there's going to be, we'll go back in if we survive for another 1,000 years. So hang on, wait a moment, we just lost 800 years of history. Oh, sorry, there's a backup. Yeah. No, but somebody's forgotten the password. So I think we're in this kind of, the internet age or the computer age is in, I mean, it's not very old. The first program ran in 1948, so it's pretty, it's not very old at all. We don't know what we're doing yet.
It's true.
It's quite fun.
Yeah. Well, Joe Armstrong, thanks so much for coming on to Software Engineering Daily and chatting with me for so long. It's been a really interesting conversation, and I'm really grateful for your work on Erlang. It's been really important in computer science.
Yeah, thank you. Yes, nice talking to you.